In this lecture, we begin a general introduction to structural equation modeling. This general introduction will span several lectures. Once we've gone through the general introduction, we'll dive into the specific topics more deeply and see how to use statistical software to build structural equation models and make inferences about them. Here's an outline of the topics we'll be covering in this general introduction. What is structural equation modeling? Why use structural equation modeling? We'll give a description of what constitutes a structural equation model. We'll then see how to specify a structural equation model. We'll then look at several examples of types of structural equation models. In particular, we'll look at an example of a path model. We'll then see an example of a confirmatory factor analysis model. And finally, we'll look at an example of what is called a structural regression model. We'll then talk about the important topic of the identifiability of a structural equation model. Now, this is important because structural equation models typically have many variables, many parameters. And in order to estimate the model, in order to fit the model, we need to be able to estimate the various parameters in that model. We'll then look at how to estimate the parameters of a structural equation model. We'll look at how to make inferences about the parameters in a structural equation model, such as hypothesis testing, confidence interval estimation, and so forth. And then finally, we'll see how to assess the overall fit of a structural equation model. Now, in this particular lecture video, here are the topics that we'll be looking at. What is structural equation modeling? Why use structural equation modeling? We'll give a description of a structural equation model. And then finally, we'll see how to specify a structural equation model. So what is structural equation modeling? Structural equation modeling, or SEM, is a general multivariate statistical modeling methodology. Structural equation modeling can be used to model the mean structure of your data, but can also be used to model the covariance structure in your data as well. And that's really where the power of structural equation modeling comes in. Structural equation models can include manifest variables as well as latent constructs. Now, structural equation modeling methodology includes as special cases a number of multivariate analyses, including MANOVA, multivariate analysis of variance, multivariate multiple regression, path analysis, and exploratory factor analysis. It also includes as special cases the general linear model, which would include regression analysis as well as analysis of variance. Why use structural equation modeling? Well, there are a number of reasons. An SEM can explicitly account for measurement error in the variables used in the SEM model. An SEM can be used to study indirect effects as well as direct effects of variables in the model. And so these two bullet points, these first two features, differentiate structural equation modeling from many of the kinds of statistical models out there. For example, some of the procedures that you've used in the past, such as regression analysis, does not account for variability in the explanatory variables. It treats the explanatory variables as being measured without error. SEM allows you to perform regression type of analyses while at the same time allowing for and accounting for variability in the explanatory variables. In addition, most of the procedures that you've looked at, or at least the way you've used them, you are looking at the direct effects of variables in the model. But SEM allows you to study the indirect effects of variables as well. Now, variables in an SEM can be fixed or random, but they can also be observable or latent. Now, there are several software packages that can be used to perform structural equation modeling. Here's a partial list. Literal and EQS were perhaps the first two structural equation modeling packages in existence. SAS has a procedure called CALIS that is used to perform structural equation modeling. The software package SPSS has a component called AMOS that is used for structural equation modeling. M+ is a standalone package for doing structural equation modeling. And then finally, the software package Statistica has the CPath component for structural equation modeling. Now, what are the components of a structural equation model? What comprises a structural equation model? Well, an SEM is a system of statistical equations defining a model that specifies structural relationships between endogenous and exogenous variables, and it specifies stochastic or probabilistic relationships between endogenous and exogenous variables, as well as between different exogenous variables. Now let's talk more about the types of variables used in structural equation modeling. You are undoubtedly familiar with the terms dependent variables and independent variables from your mathematics courses and perhaps other statistics courses as well. As you know, in statistical modeling, dependent variables are usually called response variables, and independent variables are usually called explanatory or predictor variables. Now, explanatory or predictor variables are used to model a variability in, explain the behavior of, and predict the value of one or more response variables of interest. Now, a structural equation model consists of a system of statistical equations, typically more than one equation. Each equation describes a statistical relationship between a response variable and one or more explanatory variables. A response variable in one equation may be used as an explanatory variable in another equation, and sometimes even in the same equation. So that's a feature that we really don't see in other kinds of statistical methodologies. So because an SEM consists of typically more than one equation relating the variables, the response variable explanatory variable dichotomization really does not provide a complete picture of how variables are being used in a structural equation model. And because of this, variables are also classified as being either endogenous or exogenous. Now let's look at the word endogenous. All right, the prefix there, endos, is of Greek origin, meaning of internal origin. And so an endogenous variable is a variable that is explained or predicted by at least one other variable in the model. That is, an endogenous variable is used as a response variable in at least one equation in the system. Next, let's look at the word exogenous. So the prefix exo, from Greek origin, which means of external origin. An exogenous variable is one that is not explained or predicted by any other variable in the model. In other words, it's a variable that is not used as a response variable in any equation in the system. So again, an endogenous variable is a variable that is used as a response variable in one or more equations in the system, and an exogenous variable is a variable that is never used as a response variable in the system. Now, variables used in an SEM can also be classified according to whether they are latent or manifest. Latent characteristics are hypothetical characteristics that cannot be observed directly, and therefore they cannot be measured directly. Some examples of latent characteristics would be intelligence, socioeconomic status, and anxiety level. Manifest characteristics, on the other hand, are observable characteristics that are manifested and therefore can be directly observed and directly measured. Some examples of manifest characteristics or manifest variables would be a score on a test, income, and blood pressure, because these are all things that can be directly observed and therefore directly measured. So latent characteristics are characteristics that cannot be observed or measured directly. But latent characteristics can be measured and assessed indirectly using one or more manifest characteristics. Now, the manifest characteristics that are used to indirectly measure or assess a latent characteristic are called indicators of the latent characteristic. The process of evaluating the quality of a set of indicators is called construct validation, which is answering the question or addressing the question, how well do the indicators measure the latent characteristic they supposedly measure? SEM is important in the process of construct validation. Next, let's look at how to specify a structural equation model. Now, there are two primary ways of specifying an SEM. The first is to specify it notationally as a system of statistical equations. In addition, we can also specify an SEM schematically using what is called a path diagram. And so let's first look at specifying an SEM as a system of equations. To do this, we must have an equation for each one-way, explanatory, predictive, statistical relationship in the SEM. Now, these are often called causative relationships in the SEM literature, but I'm going to stay away from that, using that word, because they use the word causative a little differently than we might use it in general. Now, in addition, we must specify information for the variances for all random variables in the system, as well as for the covariances between all pairs of random variables in the system. And this information consists either of assigning notation to those quantities or, in some cases, to imposing a constraint where we set those variances or covariances equal to particular values. So, for example, we might set a variance equal to 1, or we might set a covariance to 0. So those are the components, those are the things that you must have in place in order to specify an SEM as a system of equations. We need to have an equation for each explanatory or regression type of relationship in the system. And we also have to specify information about the variances and covariances between random variables in that system. Now, the other way to specify a structural equation model is by using a path diagram. A path diagram is a schematic representation or graphical or pictorial representation of an SEM. And there are conventions that dictate how path diagrams are constructed. And so ovals or circles are used to represent latent constructs or latent characteristics in the path diagram. Rectangles or squares are used to represent manifest variables. Error terms are represented in the diagram by their respective letters or symbols. One-sided arrows are used to represent relationships that are one-way, directional, predictive, or as they often call it in the SEM literature, causative. Two-sided arrows are used to represent relationships that are two-way, correlative, or mutually impacting types of relationships. And then finally, when we construct a path diagram, we need to identify where the parameters are that need to be estimated in the model, and we do that in the diagram using asterisks. So that's what I wanted to show you in this lecture video. I'll see you in the next lecture video.